Yo, what's up? I'm James, and today I'm going to show you guys how to do the magnetic force between two balls LeetCode problem. So, in this problem, we're given some Rick and Morty lore where apparently Rick has N baskets, where the ith basket is at position at index I in this position array. And Morty has M balls and needs to distribute the balls into the basket such that the minimum magnetic force between any two balls is maximum. Okay. So the magnetic force between two balls is at positions X and Y, right? So, or at position X and Y is X minus Y, right? So really the force is just the distance, right? And we're trying to maximize the minimum distance between two balls. And if you think about that, what that means, right? We're going to maximize the distance between any two balls. We're going to attempt to evenly distribute the balls, right? Because really all this question is asking is, so let's say this is our position array, right? This is index 0 and this is the last index, right? Assuming positions is sorted, which it's not, so we actually have to sort it. But if it's sorted, at index 0 is going to be where the furthest to left basket is, and then at the last index is going to be the right. So this is our bounds, right? If we're given two balls, right, we know that it just goes here and here. If we're given three balls, we know we have to put one here. If we're given four, then we have to put them like this, right? This is how we maximize the minimum distance. And then similarly, like we're doing like that, like with every ball, we just need to evenly space, and that is how we'd optimally solve this problem. However, we can't evenly space perfectly, right? Because we're limited by our baskets. So, like, we could have a basket here and here, and even though we want to put our third ball here, we have to pick the better of the two here. So what we could do to brute force is we could start from 1, which is as close as they could be, and go up to last position minus the first position, which would be the farthest apart they could be, and then iterate through every possible distance, and whichever one returns a maximum, or whichever one returns valid and is the maximum, then that is our answer. So I'm gonna do an example too, just so we can visualize this really well. Okay, so let's say we're given 1, right? Because down here we know lowest position goes 1. It can go up really high though, 1,000. Okay, and let's say we want to place 4 balls. Okay, so we know the bounds, right? It's 1 to 1,000. This is the farthest and this is the closest. Okay, so instead of trying every single possibility, we could just pick one in the middle, right? 500. Okay, can we place 4 balls 500 meters apart, right? We'll always start placing the first ball here, right? In the first spot, first basket, because that's just how we would get the optimal. We never leave any space in the beginning. All right, so then can we place it 100 forward? No, right? It has to be 500. Okay, so this distance is 100. Right, this distance is 100. So can we place it 200? No. Well, can we place it 700? Right, this is 300. Yes. Okay, so we can't place it here or here, but we could place it here. Okay, and then we'd see, oh, we can place it here too. Oh, but we ran out of spaces for the balls, right? We only placed 3, we need 4. Okay, so what do we do there? Well, we know now that anything bigger than this for our distance between each ball is not going to work. So we can only search now 1 to 500, right? This is literally modeling a what? A binary search, right? And we've done a couple like this now, the binary search. So let's go to 1 to 500. Now let's see. Let's pick like 250. Okay, can we place it here? So we place the first one here. Can we place it here? No. Can we place it here? No. Can we place it here? Yes. Can we place it there? Yes. Oh, but we ran out again. Okay. 125. Here? No. Here? Yes. Here? Yes. Here? Yes. Okay. So from this, we know that we know 125 works. So now we could save this and then try it again, try it better, try to optimize it even further. So now we go 125 to 250. And now we know that from this range, we're going to even out at like, we're probably going to end up at like 200, right? That's the maximum. Because we can put one here and then there, right? So our restricting our bottleneck for like the farthest we could place these was like this interval here. To do that, right? Let's write our binary search. Okay. So we'll start at 1 to position I, or position length minus 1. All right, minus this, right? So this, right, is the distance, is this farthest distance we can go. Now we can say our while loop, and we'll say this. So we'll get our mid. So this is pretty straightforward here. We say, can we place balls with this distance using this minimum distance? If we can say like our result equal to that, and then let's try to improve it. So let's try to increase the maximum or the minimum distance. Otherwise, we have to shrink the distance, right? To find where our bottleneck is, right? Because if we had like baskets like this, and we had to fit 3, this is obviously our bottleneck, right? Like we're gonna have to keep shrinking the distance until we can put balls in here. Okay, so let's write the can place balls function, right? Where we're passing the distance in, and I'm gonna call this min distance. All right, so how do we validate if we can place the balls? We know we can place the first ball at index 0. So let's do a count, and let's do a count variable. Start it at 1, and we know like our last position is equal to 1, or position 0, right? Place the first ball at the first index because that's optimal, and start with count 1. Okay. So now we actually want to loop through starting at 1 until the end of that. And okay, if at this basket we can place the next ball, place it and count that. If we can't, then go to the next one, right? So if this position minus last position greater than or equal to min distance, then we place another ball and we have to reset the last position to the index we're looking at. And basically, if we didn't place all the balls, count is going to be less than m. If we did, it'd be greater than, right? So we could just say like greater than or equal to. This will return true if we placed all the balls. If we didn't, count would be less than the number of balls, right? All right, so that validates if we can place the balls with that given minimum distance. And all we got to do now is say result is equal to -1 to initialize, and we can simply return result. Okay, and we get the wrong answer here. Like I mentioned, we have to sort this for this to work, right? It's pretty easy. We just do position sort, and we'll sort it ascending. So just remember, A comes first, we're ascending. And now we should be getting our solution, passing all test cases, and there we go. It's as simple as that. So this is a really good example of how we have to translate the wording of a question into something that we can understand intuitively and then go from there. So by them asking us to maximize the minimum magnetic force between any two balls, we had to translate that into, oh, so they want us to evenly space out the balls, right? Like that is what it's asking. And once we know that, we know that, well, we have to find the optimal number in a range of possibilities to solve this, right? And once we kind of know like these computer science concepts like binary searches, trees, sorting, etc., we can kind of use what we're given to tell us what approach we should use here, right? So once we knew that we're looking for an optimal value in a range, well, boom, that's binary search. And from there, it's just a simple verification function that, this just takes experience working with loops and counting and using counting variables and that sort of thing. We can turn this medium question or problem into a pretty easy one.